where we left off last time then? On a Friday, what's more exciting than protein characterization? Honestly, nothing.
Amanda's cell phone lost. Yeah, my cell phone lost.
You lost your cell phone?
Oh, it was a big situation Lynn and I had last night. We had to go to Target. She called it in Target. The lady was not allowed to answer it, but she felt the need to, thank goodness. And then we found it. So
Lynn saved the day.
Lynn, once again, saved the day.
Okay. So we talked about different protein characterization methods, and just to refresh your memories, we started with the STS page, or the polyacrylamide gel electrophoresis, that will allow you to see different components within the protein. If the protein has been hydrolyzed, which component was hydrolyzed. If the protein has polymerization going on, to see that as well. And we talked about different forms. Quickly, can anybody tell me the difference between these three types of electrophoresis? Yes, Amanda?
The native, you don't change anything.
Yeah. You don't change anything with the protein.
The protein.
Yep.
And so you don't really use it.
Oh, you use it if you want to see in comparison and interactions within the protein. So you do it complementary to different methods. Okay, what about the others?
Isn't it with the buffer solution? It's either SDS in it or the urea.
Yes. So if you have SDS, you are denaturing the protein and adding negative charge. So they all would migrate down the gel first based on size. If you have urea, they will be migrating based on size to charge ratio. And then you will be doing that in the lab, loading your samples on a gel, and then staining and destaining, and then looking at a different banding. And we talked about using the reducing agent, which is important for certain proteins that actually form quaternary structure with disulfide linkages. If you don't add the reducing agent, you can't really see the subunits. So adding a reducing agent will allow you to see the different subunits within that protein. So you'll be doing that in the lab. Other chemical assays, moving on to other chemical assays that we use to characterize the protein. One important one we do quite often in the lab, in our lab at least, or other labs working with proteins, is surface hydrophobicity. It's an indication of a change in the structure of the protein. So you start off as a native protein. Every protein has a certain surface hydrophobicity, but once the protein is denatured, it unfolds, the surface hydrophobicity increases. So it really relates to solubility, to emulsification. So if you want to understand a change in solubility or change in emulsification, and you want to link it back to structural change, you can look at surface hydrophobicity and compare it to other proteins, to other modifications that you've done to the protein. Let's say a modified protein versus a non-modified protein, how they differ in their surface hydrophobicity and how that impacted their structure. So it's basically a chemical assay. It's very easy to conduct. You just use a probe that can bind hydrophobic via hydrophobic interaction with the protein, and the probe can fluoresce. Then you would measure fluorescence. The more the fluorescence, the more that means the probe bound to the surface of the protein, and that means the more there is hydrophobic residue on the surface of the protein. So you won't be doing that assay in the lab, but potentially, depending on what Kati finds feasible, you might be doing surface charge with the help of Lucy, who is the expert with that. And who?
Carbon. What did you say? Zeta potential?
Yeah.
Yeah, Carmen knows how to use it.
Perfect. We have you have 40 A's now, not 2. Okay, so with surface charge, it's very important to determine surface charge. If you modified the protein, you added a group to the protein that changed its charge to relate how that charge density differs and how does that impact functionality. Again, it all boils down to how it impacts functionality. So you can measure that either by a chemical assay, or you can measure that using Zeta Sizer, an instrument that allows you to measure the charge density on the protein as well as size. That's why it's called zeta sizer. So it's a direct measure of hydrophilicity and charge and how that impacts certain functionalities. Okay. Another assay that you can do is measure of free sulfhydryl concentration. That's also a chemical assay. You know, there are proteins that have SH groups. SH group is a very reactive group. So when you heat and you have several protein molecules in the system with exposed sulfhydryl groups, they come together and they form disulfide linkages. And that means it leads to polymerization and precipitation. So you can measure the free sulfhydryl group before a treatment and after to see if there has been polymerization by disulfide linkages. Okay. Another assay which you will be doing in the lab, it's an OPA phthaldehyde assay that is based on determining the amount of free amine. So basically the amine react with an OPA reagent, and then you would measure absorption. And then what this tells you, you can use it for different things. You can use the OPA method to determine degree of hydrolysis. So let's say you have a protein and you break it down by an enzyme, you will release more free amines. And then the more free amines you have, the more you can have reaction with OPA. Then you can calculate something we call degree of hydrolysis.
What does OPA stand for?
Phthaldehyde.
What? I can spell it.
Phthaldehyde. Yeah. It's just a reagent.
Oh.
There. Okay. Another use for it, which is basically what you're going to be using it for in the lab, is to determine the extent of glycation. So you will be measuring how many amine groups have been blocked by reacting with sugar. So you will be inducing glycolysis, or you will have samples that have been incubated with a reducing sugar, and you know from your chemistry that reducing sugar, a carbonyl group will react with an amine group, primary amine group, and blocks it. So this reaction allows you to determine the extent of blockage. So you can do that to determine extent of glycation. You can use OPA to determine degree of hydrolysis. You can use OPA as well to determine the amount of degradation, let's say, in lysine upon processing. So many different applications for this OPA method. Moving into instrument-based analytical tool to determine protein structure. The one that is very common and often used is you want to determine the impact of thermal treatment on your protein denaturation. And one of the most common ways to do that is by differential scanning colorimetry. Are you familiar with this graph? You've seen it probably in food chemistry lecture, or I did when I taught last semester. Okay, so just to refresh your memory, and I don't know, are they going to do a DSC in the lab? Okay, so basically what you do is you prepare your sample in a concentrated protein solution, so you about 20% protein, and you put it in a small kind of sample holder, and then you put it in a machine, a magic machine that will induce a heat flow, and then over a time and heat, you will generate a scan, thermogram we call it. And then what you will see, if you have a protein that was not denatured and you're applying heat, the heat is going to cause a change in enthalpy. And this thermogram is going to record a change in enthalpy. So it's going to, the protein is going to take uptake energy, and then you're going to see that in the terms of endothermic peaks. So for every protein in a mixture of proteins, you will have an endothermic peak. So up here you have, for example, soy protein isolate we prepare in the lab versus a commercial soy protein isolate. What this tells me, if I look at this and I look at that, the first simple thing I noticed, this doesn't have any endothermic peaks. What does that tell me? I don't see any endothermic peaks. Are already denatured. So the SPI from a commercial source has already been thermally treated in a manner that denatured the protein. So when you run it in the instrument, you see nothing, you go, okay, the protein is already denatured. So whereas the protein we prepare in the lab with minimal thermal treatment, we see two major peaks, indicative of two major proteins in the mixture. And then what that tells me also is that the denaturation temperature of each one of them. One denatures at 75 degrees, that's the onset of denaturation, and the other one denatures at 92 degrees. So it differentiates the thermal stability of the two proteins, and also it gives me the enthalpy. You can see that, for example, the enthalpy is also an indication whether the protein has been partially denatured or more denatured than another protein. So let's say I take that protein and I treat it, heat treat it, and run it again. I can see the delta change will be smaller. I'll get smaller peak. So the protein will be partially denatured. So what I'm trying to say is with this method, you can determine extent of denaturation, onset of denaturation or denaturation temperature, and determine whether or not the protein is already being denatured. So it's a very powerful tool. We rely a lot on it in the protein ingredient world. Other methods to assess degree of denaturation, again, which is a very key aspect in protein functionality, you can use spectroscopy. One is Raman spectroscopy. And here's an example from a research we've done in the lab. In Raman spectroscopy, basically it's an IR based. So you're looking at vibrational energy and the vibration energy of the bonds. So each peak or band you see a different wave number is related to a certain bonding or functional group. So every protein will have a unique scan or unique spectra, we call it. That's, if you remember in food analysis, it's spectra. And then for this, for example here, we look at whey protein isolate non-heated, and with H that means heated, at different pHs, and you look at the changes shifting in the bands and changing the intensity of the band to know what changed in the protein structure. So we use it, in this example, we used it to differentiate a modified protein to a non-modified protein. A modified protein, we modified it in a way that induced thermal stability. So when a modified protein was heated, you see the spectra does not change, the banding does not change at any pH compared to the native non-modified protein. When you heat at different pH, you can see obvious changes in the banding and which relates to changes in bonding and functional groups. So that is a powerful tool. Another tool is FTIR, and this is mostly used in the protein world to look at secondary structure, changes in protein secondary structure. And usually the protein secondary structure is within the bandwidth of 1700 or wave number, 1700 to 1600. We call that the amide 1 region. So this is one peak. You see it as one peak, but it really represents several secondary structure assignment. And usually you do some mathematics to deconvolute the peak and determine beta sheet, random coil, alpha helix, and beta turn. A lot of ways to determine, for example, degree of denaturation of a protein, they look at beta sheet to alpha helix ratio. So the change in beta sheet to alpha helix ratio is an indication also of change in denaturation of the protein. Well, this is another way to look at denaturation indirectly by doing gel electrophoresis. And here, you're not really looking at degree of denaturation, you're looking at polymerization, which is a consequence of denaturation. So basically if you have a protein, here's in this example is whey protein, beta-lactoglobulin, alpha-lactalbumin. You heat it, let's say for 10 minutes, 20, 30, 40, 50, and 60 minutes at 75 or 80 degrees C. And then we load it again on the gel. And you see that, of course, the protein is being denatured because both proteins denatured at 70 or below degrees Celsius. So when you heat it above 70, they're going to denature. And once the protein is opened up, it will expose hydrophobic groups and also sulfide groups. So then the protein will have more tendency to be attracted by hydrophobic forces to each other and then forming disulfide linkages. And then you start seeing polymerization. So this is an indirect way of, first, the protein is denatured, but it's really a direct way to looking at forming of polymers. These are polymers because, in a gel, they're all moving down based on size. So larger ones will not go down through the gel. Okay. So here in this example, the more you heat, the higher the intensity at the bottom, at the top, sorry, and then the lower the intensity of these monomers. You can see they disappear from here and they form polymers up here. So other ways of determining denaturation, you can do UV absorption and fluorescence. So what are the three main amino acids or the three amino acids that are hydrophobic and absorb light, not just hydrophobic? Tyrosine, tryptophan, phenylalanine, and tyrosine. So three of them are hydrophobic and they absorb light and fluoresce. But because they're hydrophobic, they're mostly on the interior of the protein, so within the interior moiety hiding from the aqueous medium. So when you denature the protein, it's going to open up and they're going to be exposed. So when you measure absorption and fluorescence, you're going to have higher fluorescence because they're exposed now. So you will see higher measurement. Solubility is an indirect assay to determine denaturation because there is a direct correlation between denaturation and solubility, or I would say negatively correlated. So the more the protein is denatured, the lower the solubility is going to be, because in general, theoretically, when the protein is denatured, hydrophobic groups are exposed. They don't like water. They tend to associate with each other, polymerize, and precipitate. Digestibility is also an indirect method of denaturation because when the protein is denatured, partial denaturation actually has a positive impact on digestion because the protein is opened up. You have the digestive enzyme will have easy access to the sites of hydrolysis sites. So you will have enhanced digestibility. But when you have a polymerized protein, you have a big blob of protein, then the digestive enzyme will have a hard time getting there and digesting. So you will have a reduction in digestibility. Activity in this case, for example, enzyme activity. Enzymes are proteins. So if the enzymes are denatured, you will see reduced activity. Okay, other forms of instrument-based analytical tools. So we talked about structural deviation, meaning looking at structural changes, DFC, FTIR, or Raman. But when we're looking at aggregation, other than gel electrophoresis, you can do size exclusion, HPLC, MALS. MALS stands for multi-angle light scattering. Light scattering is a universal detector, a very powerful detector in terms of detecting non-specifically. So with size exclusion, from what you remember from for the analysis, you are separating based on size. So if you have dimer, trimer, large polymers, and monomers, you can separate them by HPLC and determine the extent of aggregation that you have in your system. You can look at morphology using microscopy, different forms of microscopy. One is transmission scanning electron microscopy, looking at how the aggregates look like or where are they located. if we're looking at a complex matrix of food, such as after we gave the example of extracting oil, let's say from soybean meal, or extracting oil from canola, and then you end up with a meal. You can look at the protein morphology in that meal to see how easy you're going to able to extract them or solubilize them. So you can do that. Chemical deviation, that means changes in the protein, whether you hydrolyze the protein or you glycate your protein. You can use MALDI-TOF. For this, for example, you can determine the size of the protein, molecular size, the actual molecular size of the protein, and you can also determine what happens to the protein upon enzymatic modification, or at which site on the protein a sugar bound, for example. LCMS is mostly used for identification purposes and sequencing. If you're looking at the sequence of a particular peptide, you can do that with LCMS. So you won't be doing these in the lab, but it's good to know. It's good to know them and know the purpose of them. You might encounter them in a different life or different place. Okay. Moving from structural, we go to protein functionality. So in the lab, you're going to do some structural characterization and functional, and try to link structure to function. So one of the tests that you'll be doing is protein solubility. And the way you do that is simple. You prepare a protein solution. Oftentimes it's in water. Sometimes we adjust the pH of the water. Sometimes you dissolve it in buffer to make sure that the pH is constant. And then let's say you prepare a 1% protein solution or 5% protein solution. Make sure it's well mixed, well hydrated. And then to determine solubility, you apply centrifugal force. So you centrifuge your sample. Proteins that are not very soluble, they're going to precipitate. And soluble proteins are going to remain in the supernatant. So how would you determine the soluble protein? You would take the supernatant and measure the amount of protein you have in the supernatant and relate it to the original amount of protein that you had in your sample. How much of that original protein was soluble? So you can use methods like KELDA or DUMAS or any colorimetric method if you don't have interfering substances to determine the amount of protein in your sample. What are they going to do in the lab? They're going to do DUMAS. That's my favorite choice. So one example, and I think you're going to do something like that in the lab. So looking at whey protein isolate solubility, what you can see here from this graph is that's whey protein isolate, and you have pH, and then you have relate to percent solubility here. Okay, so when the protein is in the native state, that means you have the, let's say your protein is globular, take beta-lactoglobulin as a model. It's very hydrophilic on the surface. So it's going to be soluble over a wide range of pH. Even around its isoelectric point. What's the isoelectric point again? Huh? What? What did you say? Oh, 4.6, that's for casein. But what happens to the protein at the isoelectric point? Neutral charge. So it carries zero charge. So when the protein carries zero charge, what forces would dominate? What interaction forces would dominate between the proteins? Would be dominant. Hydrophobic. So you don't have repulsion. You don't have a net charge. So you will have a very strong hydrophobic interaction or dominancy of hydrophobic interaction. But if you start off with a protein that's already very hydrophilic on the surface, even at zero charge, they will still interact with water, okay, more than attracting with each other because they don't have a lot of hydrophobicity on the surface. So you see a slight dip around the isoelectric point, but still they remain soluble. However, once you heat the protein, and this is very interesting, once you heat the whey protein, it's going to denature. Now, we have hydrophobicity on the surface. So you would measure surface hydrophobicity, for example, you'll see it's higher. So when you have charge at low and high pH, even if you have some hydrophobic groups on the surface, you have quite a bit of repulsion, you don't get polymerization, you still have solubility. But when at the isoelectric point, you have zero net charge, those hydrophobic groups are exposed, you don't have repulsion, you will have attraction between the proteins, and then they will precipitate and the solubility will go down. Okay? So hopefully your results in the lab will project or reflect this, this theory, which is true in most cases. This is from a research we've done. We looked at whey protein isolate and we looked at the glycated whey protein. We'll talk about glycation later. It's modification of the protein to make it more soluble. Look at heating at pH 4.5 and 5.5. It lost solubility, same as what this figure shows. However, the glycated protein, even at the isoelectric point, it's still 90% or higher soluble. So this showed you the effect of modification on solubility at different pHs. So that's an example where solubility is used to look at the impact of modification. Okay? In this example, modification resulted in improved solubility at the isoelectric point, even after heating. Questions? Okay. Another functional property you're going to measure in the lab is water holding capacity. In food chemistry, we talked about water binding capacity and we talked about water holding capacity. Do you remember the difference between the two? Yes, entrapped in a protein network, I would say. So like a gel. So when you have protein that form a network with water that is entrapped within the network, represent the water held within that network. So it represents the water holding capacity of that network. The water binding capacity is the actual binding of the water with the protein molecules via a dipole interactions or hydrogen bonding, or even physically entrapped within the molecule of water. So the water can penetrate and fits within the gaps of the protein itself, not the network. Okay. So in the lab, you're not going to measure water binding capacity, but people use to measure that as well. But you're going to measure water holding capacity. So it's a very simple, fun test to do. You just prepare a protein solution. Usually we do it at neutral pH, but you can do it at different types of pH depending on testing for different food systems. But in the lab, you're going to do it in water. Do they adjust the pH? So just water. So water is between 6.5 pH. And what you're going to do is you're going to heat the solution. Usually you're preparing it at a specific protein concentration that will actually form a gel. Different proteins will form a gel at different protein concentration. Gelatin, for example, you can form a gel at 1%. Whey, for example, you might need 10 or 15%. 10%. Yeah, and soy about 12 or 15% as well. So different proteins, you require different concentration for them to actually form a good gel for you. So you're going to prepare solutions at different protein concentration depending on your protein assigned to you, and you're going to heat it. So you're going to thermally induce gelation. So you heat the protein to denaturation temperature and above, so that the protein is denatured, and you allow enough time so that there will be a network of protein formation via hydrophobic interactions and disulfide linkages. Also, it can happen if the protein has sulfider groups. And then a network is formed and water is entrapped. You take that tube, invert, and the water drops might fall out or not. and then you measure the weight of the tube before and after, and then you put it in an equation and determine water holding capacity. Why is water holding capacity is important? For example, here's an example of a real application. That's a burger, a beef burger, not necessarily a burger, a beef patty. And then this is another beef patty formulated while adding whey protein to it. So this is without whey protein and this is with whey protein. So you cook and then you leave it, syneresis happens. Syneresis, water and fat can actually drip out of your patty. However, when whey protein was added, it enhanced the water holding capacity upon cooking as well as the emulsification. So fat and water were held better. And this is how you would do it in a lab to determine in a real system how much water or fat you lose. You get, let's say, the meat, ground meat, you measure the fat and moisture of the ground meat, you cook it, let it sit overnight, and then you measure the water and fat phase separated. So you did that on a lab scale, in a lab experiment, and then you did that in a real application. But you're not going to do beef patties in the lab. Now, measuring of gelation or gelation strength is something else that you're going to do in the lab. It's similar to measuring water holding capacity. You are forming a gel, so at a specific protein, specific heat treatment and time. You form a gel, but here instead of flipping the tube and measuring the water dripping out, here you take the gel out of that tube, you release it from the tube, and then you use a texture analyzer, which you will be using, to determine the force needed to break that gel. So the higher the force needed to break the gel, the higher is the strength of the gel. Then you can compare different gels from different proteins that way. What impacts gel formation? Gel formation is affected by several factors. What do you think affects gel formation? Huh? Heat? Okay, if you heat to a temperature below the denaturation point, it's going to take forever for the gel to form. It takes longer time, and it might not form. So you want to make sure you heat to above the denaturation temperature of the protein. Good. What else? Who said that? Yes, concentration of the protein. Different proteins require different concentration to form a strong network. Perfect. What else? pH. So you don't want the pH to be at the isoelectric point. You'll get a very gritty, granular gel. And you don't want it to be at the extreme. You won't get the protein to interact at extreme pHs because of the high net charge. You want somewhere in the medium, around the isoelectric point, a little bit further from it, and not too much of a charge. What else? Yes, salt concentration. Good. So again, salt concentration, a little bit of salt can help facilitate interactions between the protein and interactions with water, because the gel is really a protein-water protein interaction. So a little bit of salt helps. A lot of salt, again, you're going to have a gritty texture, same with a pH around the isoelectric point. You don't want a lot of salt, you end up salting out, having aggregation, salt competing with water for interactions. Good. All right. The other thing you're going to measure in the lab is emulsification property, but one property in particular, which is emulsification capacity. Measurement of emulsion, you can measure the capacity, which is really measurement of the amount of oil that can be emulsified by a known amount of protein. We can usually say amount of oil per 1 gram of protein. That's usually the unit. So how much oil 1 gram of protein can emulsify? So that's your emulsion capacity. There is emulsion activity and emulsion stability. You're not going to do that in the lab, but the emulsion activity is basically how quick the protein can emulsify or get to the surface, how surface active is the protein in order to form a film around the droplet of water. Usually it's a spectrophotometric method. And then stability, you can do it also spectrophotometric method, looking at the absorption over time to see how the emulsion changes over time or destabilize over time. Or you can simply look at separation phase or creaming, rate of creaming, or you can look at the size of the droplets over time. You can do that by measuring droplet size. And if you remember from your food chemistry, the creaming starts with flocculation, coalescence, and then separation creaming. So you're not going to do that. You're only going to measure emulsion capacity, which is basically a titration into a protein solution with oil. So you will have kind of a very big burette, and you'll have corn oil in it, and corn oil with Sudan red, so that you have this beautiful pink color. So you can differentiate the formation from the break of the emulsion. Again, Lucy might serve as a TA for this method. She's done that a lot in the lab. So basically what you do is you titrate oil at a very specific speed and controlled speed, and then you have your protein mixture, and you have a shaft in there, or what do you call it, a homogenizer in there that continuously mix your oil with the protein solution, and then you form an emulsion. And then you continue titrating, and the emulsion is hopefully consistent for a while until the last one drop causes the emulsion to break. We call that inversion. At the time where the emulsion goes from smooth to gritty and broken, that would be the end of your titration. You determine how many milliliter of oil you were able to titrate with whatever amount of protein you had, and then you calculate milliliters or amount of oil per 1 gram of protein. So again, what's emulsification is affected by what factors?
pH.
Again, yes, pH. So the pH impacts emulsification. Again, if you have too high of a pH or too low of a pH, you have a lot of charge. For emulsification, you need a balance between hydrophobic and hydrophilic residues on the surface, because you want your protein to interact with the oil, and you want your protein to interact with the aqueous, hence emulsify. Okay, so you don't want extreme, and then those proteins will not form a nice film around the bubble. They will repel each other so much they won't form a film. Not the bubble, sorry, the oil droplet. Other than pH?
The speed or the amount of force that you're putting into to emulsify it?
Definitely. I wasn't looking for that answer, but definitely the speed is very important to be controlled. You don't want to have actually denature the protein by a lot of force.
The
Character of the protein.
so if it's more balanced, maybe it's hydrophilic.
Yes, perfect. So the actual structure of the protein and the balance on the surface. We call this a surface property. So what's on the surface? A balance between hydrophobic and hydrophilic. The structure of the protein, casein is an open structure. It's readily associated on the surface of the protein, on the surface of the emulsion, and has the hydrophobic and hydrophilic balance. Whey protein, for example, is a globular protein, very hydrophilic on the surface. It won't form a good emulsion unless you denature it a little bit, so that you open up some of the structure and expose some of the hydrophobic groups. Anything else?
Question.
Yeah.
So for this analysis, will we set a certain oil as a standard?
You know, you're very clever, or very clever question. And clever too. So yes, oil has a very important impact. We usually use the same oil when we are looking at differences between protein treatments or differences among different proteins, we tend to use one oil. So in the lab, you're going to use corn oil. But let's say corn oil will have a different fatty acid profile, and then another oil will have another set of fatty acid profile. The way the protein interacts based on the profile is different. Yeah. So good. Good. I wasn't looking for that, but that's good. Anything else? I don't know if I missed anything else. Yeah. Yes, temperature would affect the stability of the emulsion. Usually when you form your emulsion, you don't need heat to form the emulsion. But definitely if you process the food after emulsion, yes, it depends on the stability of the protein that is around that oil droplet. Okay, one last thing. I don't know if Kari is going to include the foam, but it's another simple measure. If time permits, we will do foaming as well. For foaming, it's really simple. You measure foam volume and foam stability. That by foam volume, you can measure either the overrun, that means how much foam generated or volume of the foam generated with respect to the volume of the initial liquid. So you can calculate foaming that way, or you can measure foaming capacity. And I think the method we have, the SOP in the lab measures foaming capacity, which is milliliter of foam that is generated using 1 gram of protein in solution. And then there's the foam stability, which is over time you measure that foam volume and see how it's going to shrink or change, because the bubbles will coalesce eventually and break. It'll become larger and break over time, so you can measure that as well. Let's recap before we head out. I think after that it's protein modification. Okay. So let's relate structure to function a little bit. So if you have a protein that is globular and native and has low surface hydrophobicity. In this example, this is beta-lactoglobulin model. Then it will be what of these?
Solubility would be good.
Have good solubility. Anything else? Not really. Okay, so good soluble protein. You reduce, it's not reduced. Is it less functional than another protein? Yeah.
Yeah.
Okay. Partially denatured? What happens? Very good. You improve digestibility. It's partially denatured. Digestive enzyme will have access. What else? Better emulsifier. Very good. You have exposed some hydrophobic groups. You have a better balance on the surface between hydrophilic and hydrophobic. What else? Lower solubility than the native, because now you have hydrophobic groups exposed, you have cysteine group exposed, you can form hydrophobic interactions, and you can form disulfide linkages. What else? What do we need to form a thermally induced gel? What does the protein need, what needs to happen to the protein to form thermally induced gel? So when you denature the protein, you can, with heat at a constant rate, you can form a gel. So you will have better gelling agent. Let's see. Yeah, I think that's it. Now it's denatured and it's polymerized. You have an aggregate. Lower solubility, for sure. Reduced, have oval or reduced functionality. Mallory?
Would the digestibility also be reduced?
Yes. Because now you have a big blob of a protein aggregated together. Enzymes will have a hard time reaching sites. Very good. Good stop. We can continue on Friday. Not Friday. Today is Friday.